Welcome back YouTube. In this video I'm going to show you how you can bias any transistor, and I'm going to explain some more basics about electronic components, and we are going to make a new type of distortion pedal that I will design during making this video. Okay, let's start with the absolute basics. What is electricity? Electricity is a bunch of charges moving around. If I have a battery like this, then they want to go from the negative terminal to the positive terminal. If I play my guitar through an audio cable like this one, then they want to move back and forth from the tip to the ground, and they do that back and forth based on the frequency that you're playing. So if you're playing an 80 Hz E, they want to go back and forth 80 times per second. Inside of a piece of wire, charges are free to move around, and we say that the voltage across any piece of wire is always the same. If I put a piece of wire across this battery, then charges will move around very quickly and they will smash into the battery and heat it up and damage it. So we need a way to control the charges when they move. We do that using resistors. This little blue thing is a resistor. What it is made of is a piece of resistive material that is very carefully measured to have an exact resistive value. To illustrate resistive materials, I have this pencil. Pencil is made out of graphite. Moving through graphite is a lot more difficult for charges than moving through metal. We can measure resistance using a multimeter. Measuring across this pencil gives us a value of about 22 ohms. Although it's hard to say because the contact points of the multimeter change the value a lot. If we halve the size of our pencil, it should halve the resistive value. This seems to be about 10 ohms, so that should be correct. If we measure the resistance across this little resistor here, we see that it's about 900 ohms. Earlier I said that electricity consists of moving charges. So charges are measured in coulombs. 1 coulomb is approximately 6.2 times 10 to the power 18 electrons. Or rather the lack of this many electrons, because a coulomb is a positive charge, whereas an electron has a negative one. When I connect my 900 ohm resistor to my 9-volt battery, we can calculate the amount of electrons that are flowing through the system using what's called Ohm's law. Ohm's law says that the current running through it, denominated with the letter I, is equal to the voltage divided by the resistance. Our resistor has 900 ohm, which is equal to 900 second volts over coulomb. If we divide 9 volt by 900 second volts over coulombs, then we get 0.01 coulombs per second, or equivalently about 6.2 times 10 to the 16 electrons per second. Meaning that if I connect this resistor to this battery, this many electrons are flowing from the negative terminal to the positive terminal every second. The electrons themselves don't move that quickly though. It's just the flux of electrons going through every part of this circuit. Next up, let's talk about these potentiometers that you see everywhere in audio effects. They have 3 pins. The pins at the edges are just connected through a resistor. In this case it says 50K, which means it's a 50,000 ohm resistor. If you imagine our resistive material from earlier, a potentiometer is very much like this piece of graphite with a connection at the start and at the end, and then the middle pin is connected to a third connection that can move throughout the piece of graphite, cutting the resistance in 2 pieces. Thus, when the potentiometer is like so, these 2 pins connect directly, whereas there's a 50,000 ohm resistance between these 2 and this pin. Whereas if I put it in the middle, there's a 25,000 ohm resistance through the left and the middle pin, and a 25,000 ohm resistance between the middle and the end pin. If I go all the way to the end, these 2 are connected and there's a 50,000 ohm resistance between this one and the middle. When we draw circuits, you probably have seen batteries being drawn like so, with this being the positive terminal and this the negative. Often you also denote the value. I'm not going to use this notation, however. I'm going to put an arrow that says 9 volt when I connect to the positive terminal, and when I connect to the negative I will write down a ground symbol. A resistor is drawn with a squiggly little line. If I place two resistors like so, then the resistance of the whole circuit will add up the resistances of these two resistors. I should also write down the values of these resistors. Let's say this one is 1k ohms. You never write down the ohms because the resistance implies it has ohms. And let's say this one has 500 ohms. For some reason we don't write ohm but R in circuits when a resistor has a value that is less than 1000. And we connect a little wire here. Now the thing that we're going to make use of is that Ohm's law does not only apply to the whole resistance being 1.5k, but it also applies to each individual resistor. It also tells us that the voltage is equal to the current multiplied by the resistance. Let's make our supply 10 volts to simplify calculation. The total current can be calculated as 10 divided by 1.5k, 1 over 150 ampere. Ampere is just coulomb per second. Now the thing we care about is the voltage at this wire here, compared to ground. When you measure voltage in a point, it always means compared to ground. We can calculate it by using Ohm's law on this 500 ohms resistor and using the total current. So our voltage is equal to 500, and here I mean this voltage in the middle, let's call it Vm, is 500 divided by 150, multiplying this and this. And that's going to be 3 1/3 volts. If we replace these resistors by R1 and R2, and we replace this voltage by Vt for total voltage, we can calculate in the general case that our voltage in the middle is equal to the total voltage multiplied by R1 divided by the total resistance. This is called a voltage divider, and it will be crucial to understanding the amplification circuit we talk about in this video. So here we are back in our circuit simulator, and we just saw a bunch of resistors and how they work. So let's test it out here. If I click draw and then passive components, potentiometer, I can make a potentiometer. It's currently at 1000 ohms, but if I click edit, I can make it 50,000. And here I can change the middle pin. If I click draw, inputs and sources, add voltage source 1 terminal, I can go to 5 volts, or I can edit this to 9. If I click G on my keyboard, I can make a connection to ground. So now you see a current flowing through here. This circuit is equivalent to the circuit that you would get if you replace this variable resistor with two resistors that are the exact same value as the resistor over there. So these two circuits are equivalent, just to illustrate how the potentiometer works. Only this left one I can move around easily, and this one is static. Because Ohm's law doesn't only apply to the combined resistors with the 50k ohmage across them, but also to each individual resistor, we can calculate that the amount of voltage on this pin has to be at the percentage that these two resistors divide. So in this case, 9 times 14.6 divided by 50. So this creates what is known as a voltage divider. If we measure the voltage at the pin at the end, we can see that moving the resistance around moves it in between 0 and 9 volts. The next basic electronic component we'll talk about are called capacitors. This here is a very old capacitor that I got from an old radio. What I like about this one is that you can see what the capacitor is actually made of, because they used a translucent film. A capacitor consists of two metal plates that are very close to each other but do not touch. These two pins are connected to the two plates, and so you cannot run electricity across it, but because the charges can still apply forces to each other across the plates, if you run an AC current, it actually does pull charges through. The symbol that we use for a capacitor is two lines that barely don't touch, symbolizing the plates that are inside of the capacitor. Capacitance is measured in farad. You will often see capacitance values written without a unit next to it, like so. And what is meant then is microfarads. In other words, this would be 10 to the power minus 7 farads. And 1 farad is equal to 1 coulomb per voltage. And this stands for the amount of charge that accumulates across the plates when you put a steady voltage over them. Here you see an AC current running through a capacitor. The DC current is blocked, and in this case, even though there's no direct connection between the two wires, because the capacitor can temporarily store the charges, it looks like the current goes through. If I click Reset Simulation, you can see that initially there are some charges being stored on the capacitor with the DC current. If we compare the voltage after the capacitor with the voltage before the capacitor, we can see that it traces a circle. However, if I lower the frequency of the supply and I increase the simulation speed a bit, you can see that the voltage drops drastically at the lower end. That's the y-axis in this case. Because the capacitor is not able to fully transmit all the charges over the time that the signal takes to switch. If you think about a DC current as an AC current with an infinite wavelength, then this makes a lot of sense. Alternatively, I can also lower the capacitance of the capacitor. This is equivalent to making the plates on the capacitor smaller. Now the capacitor is not able to hold enough charges to let the 60 Hz signal through. However, if our signal was an incredibly fast signal, the smallness of the capacitor is not so relevant. Capacitors can come in all sorts of shapes and sizes. These 3 capacitors are all bipolar capacitors. However, these huge round ones are called polar capacitors, and they can only be used by putting the negative voltage across them at the pin with the gray line next to it. Polar capacitors use some special materials which make them able to have way more capacitance than an apolar capacitor. On to transistors. Transistors have 3 pins that all do something unique. Every transistor has a little serial number that describes the type of transistor that it is. They have a flat side and a round side, which allows you to look up the orientation of the pins. Unlike capacitors and resistors, there's a lot of variance with every transistor that you find. There are 3 common types of transistors. Bipolar junction transistors, metal oxide semiconductor field effect transistors, or MOSFETs, and junction field effect transistors, or JFETs. Additionally, all 3 of these come in 2 polarities, where the other polarity changes the direction of this arrow. Looking at your transistor, you wouldn't be able to tell that this is a BJT with reverse polarity and this is a MOSFET. The only way to tell is by looking at the code and looking up the datasheet. The simplest way to understand transistors is to view the top and the bottom pin, which are called the collector and the emitter, or the drain and the source, depending on your type, form a one-way pathway for current that is only available if a condition on the base or gate, depending on the type, is met. Let's look at the following diagram. Here we have a transistor with a resistor that is put on a path from high voltage to ground. If this path would be open, then current would flow through the resistor, and the amount of this current can be calculated using Ohm's law. If no current through this transistor is restricted, then the voltage at this point would be the same as the voltage to ground. However, if no current can flow through this transistor, then this transistor would do the exact same thing that you would expect a resistor with infinite resistance to do, meaning it forms a voltage divider with this resistor, where the voltage at this point would be the same as the high voltage. However, crucially for our purposes, a transistor can also partially let current go through. Let's move to the simulator to see how this works. Back in the simulator, I have my NPN BJT. What happens here is that if this wire would be open, then we would see some current flowing through this resistor. But the transistor doesn't allow that, because there is no voltage at the base. We are measuring the voltage at this wire, And since there is no current running through here, it's at 9 volt. Because you can see this transistor as an infinite resistor. So with an infinite resistor here, if this would be a voltage divider, 1 is 0% of infinite. So we are exactly at 9 volt. If we introduce our old voltage divider with a potentiometer and we connect it to the base, we can see that the voltage now depends on the voltage at the gate. If there's no voltage on the gate, the voltage here is maximal. But if I increase it, it very quickly drops to 0. As you can see, we only care about this little part of our input voltage. The way we can fix that is by adding a static resistor in front of our voltage divider. So I made this static resistor 80k, and now you can see that with this tiny change of voltage at the base, we can induce a large change of voltage at the collector. 0 volt at the collector, 9 volt at the collector. Even though this voltage only changes from about 0 to 0.6 volt. So we've inverted our voltage, but we've also multiplied it by a factor of about 13. The only thing we have to do is to balance this voltage at the exact midpoint, so that would be 4.5 volt. So now if we add a guitar signal on our very sensitive voltage regulator, we can see that it already blows it up a lot. This is a breadboard. This one is filled with components. The way that these work is that there's these long horizontal lines that you can easily connect to power, and then there's small vertical lines, and they just connect together using these little connector pins. These things are useful because it's very easy to put components into these pins when there's plastic supporting them, and you can very easily take them out and they will make contact. If I pull off this sticker, you can see how all the connectors in the breadboard are aligned. So the first thing we'll need to do is to choose the type of transistor that we're going to use. I got this little assortment here. Last video I used this one, but this video I want to change it up and I'm going to try to use a PNP resistor. Let's go with this A1015. So of course the first thing you want to do is to look at the datasheet, and I believe this is it because this is the one I found when I looked for the name. You can see our current rating is minus 150 milliampere, and that makes sense because it's a PNP, the current goes the other way around. Our HFE seems to be from 70 to 400. The datasheet is a bit vague because I don't know if this is from the top or the bottom. Since we can see the pins on this picture, I guess you're looking at it from the bottom. Then it tells you that the leftmost pin is the emitter and the middle one is the collector and the right one is the base. So we've got our breadboard here, and I'm going to do something that might look a little bit weird. I put my positive end in the negative rail because I'm just used to the negative being ground, and the positive will be minus 9 volt now because we're working with a PNP. So we need a negative voltage to supply our circuit. I also connected these rails with these ones on the bottom here. So I've got my A1015 here, and the datasheet said that pin 3, this one on the right, is the base. So that one actually will take the guitar signal. So I'm going to put the base on the left of my breadboard because I like to read them from left to right like a book. Then I got this audio connector here that I put some lugs on. So this orange one is connected to the tip of it, so that has to be the input signal. Let's put that over here. And then the other one, of course, needs to be connected to ground. Okay, now for the input capacitor, I'm going to use a tiny capacitor. This has about 52, that means it's about 5 nanofarads. So this input capacitor will go from our input to a new connection, and then here we're going to need a voltage divider. To set up the voltage divider, I'm going to connect the 2 rows next to it to negative and positive voltage. And then I'm going to use a 1 million ohms trim pot. 10.5 means 10 times 10 to the power 5 is 1 million. And that's going to be our voltage divider. I'm going to put it on about 10% to just raise the voltage a tiny bit, or lower in this case. And of course the output of our voltage divider has to be connected to the base of the transistor. The next thing I'm going to set up is our gain resistor, and for that I'm going to use a 1K trim pot, and our emitter is the rightmost pin on the transistor, so I'm just going to connect this gain directly to the emitter. Now I need a little cable that goes from the trim pot to ground. So I'm first going to measure out how big that should be approximately, and then I'm just going to cut it off with this little, and I need to pull off the ends. I always use my teeth for this. So this will go from our trim pot to ground. If I turn this all the way here, my emitter is directly connected to ground, but if I turn it like so, then the emitter is connected to ground through a 1K resistor. So this is now our gain control. For the bias I'm using a 100K trim pot. To make some space I jump the collector across, and I'll connect this to the middle lug of my trim pot. So our emitter needs to be connected to our voltage supply, which is minus 9 volts in this case. So the only thing we need now is an output capacitor, and I'm going to use this 224, which means 220 nanofarads. Going to snip off the ends, and this has to go from the collector to our output. So I'm just bending it in shape. So with all of that in place, let me grab my output jack. I've got another one of these. Connect the ground to ground. Connect the feely bit to the output. And I can connect it to my guitar. Let's hear what it sounds like. Okay, so I hooked up my guitar and a battery and the output to my PC. And now if I play my guitar, you will hear nothing. And that is because the output voltage is a bit too high or too low. So now you do hear it. Now we can see what it would sound like if we bias it wrong. So you can already hear some distortion there. Now I did do something here that I told you explicitly not to do in the last video, and that is if I would now turn my bias and my gain in such a way that there is no resistance in the path through the transistor, then it will actually catch fire. Don't do this at home, kids. I was testing the prototype that we just built on these two different guitars, and then I realized that they sounded very different. And that's because a huge factor with this design is that the voltage of the guitar itself creates a huge swing in how much this circuit actually distorts the sound. Because of this, I think the best idea is to make a second amplification stage so that we can more accurately tune the input voltage of our signal. If we want to design a proper preamplifier, it's a good idea to know what sort of voltages we are working with. So I set up this little peak detector that should hopefully tell me what the voltage of my guitar is. It says 1.017 volts now, but if I play, it goes up all the way to 23. That means our guitar is about 6 millivolts peak to peak. Trying out my other guitar that I suspect has a higher voltage, we can see if I play it, it jumps all the way up to 1.1 volt. In case anyone is wondering, I think the difference in voltage in the guitars is because in the ignorance of my youth, when I made the body of this red guitar, I did not implement a way to increase the height of the pickups, and they're very far away from the strings, whereas with this other guitar, you can see that they're actually quite close to the strings. This is the preamplifier that I came up with, and there's a lot going on here, so let me walk you through it one by one. First off, there is this bias control that changes the voltage divider at the start. The way we're going to want to bias this is at this point our signal can swing between 0 and -9 volts, and we want it to sit exactly in the middle when we're not amplifying. So I'm probing this here. I'm going to change the bias so that this says -4.5, and in a bit we'll see how we're gonna do this with the real circuit as well. So now it says approximately 4.5, and what we want to see is that this is also 4.5 if we change the beta value of our transistor. So our preamplifier should not change a lot depending on this beta value, because it can change so wildly. So this is going to be a trim pot in our final design, and it's just going to take care of small errors in the resistors in the circuit. Next up, let's remove the bias now that we know that it's approximately right, and look at the output signal. In the scope, I pressed show peak to peak and show spectrum, and here it says P to P is 55 millivolts, which is already an amplification factor of almost 10. But if I crank up the gain all the way, then we see the P to P is 600 millivolts. So that's an amplification factor of 200. That's pretty good. You do, however, see this tiny blip here on the red spectrograph. That means that there's a tiny bit of distortion in our signal, but I'm not too worried about this. Now let's take a look at the stronger signal with the gain turned down all the way again. So when I apply my strong signal, you can see the peak to peak is already at 1.7 volt with an extremely low gain. So unfortunately our gain won't be able to pull us through the entire way, but we can use the volume knob on our guitar to make the strong guitar a bit weaker so that it's also in the range that we want it to be. I mostly care about this specific distortion pedal working with this guitar because that's the one I use mostly. What is good news is that our strong guitar signal with the gain all the way seems to have very low distortion. Now if you're an actual electrical engineer, as I've been told by one, then you can actually use information about transistors and their linear region to calculate how to not get any distortion, but that goes a bit above my expertise. I can't find any very coherent information on this. I also have some trouble deciphering these graphs for the datasheet of our transistor. Anyway, I have faith in that this is going to work. So let me talk a bit about the reason why I set it up like so, with this gain control being controlled by a capacitor. By the way, if we turn up the gain all the way with our strong guitar signal, you will see it distort a lot. So we can already make some distortion with our strong guitar with this, but I'm going to use it as a preamp, and that is also going to control the distortion later in our circuit. So why did I set it up with this capacitor like so? Like why didn't I make, for instance, this resistor be the gain control or have this short to ground immediately? The reason for this is when you change these resistive values, the bias voltage for the transistor also changes. But if you do it like so with this capacitor here, then this bias voltage stays around the same value because the bias is set by the DC current going through the transistor. So having a lot of AC go through here doesn't change the voltage at this point a lot. So I'm doing a voiceover over a time-lapse of me assembling the preamplifier. Here you see me setting up the gain, and remember that since the polarization is reversed, you should put the minus of the capacitor to the circuit. And if you, yeah, here I set up the bias measurement. And if you want to know what the vibe was. Bedamme wat vandaag, zandanden vol met wind. Nee, zo. Geef die boer een stoel. Okay, so I just assembled the prototype. And remember how we had to tune the bias? Oh, I put it on 10 amperes instead of 20 volts. Stupid of me. Remember, since this is assumedly a 9-volt battery, let's actually first check the battery voltage. So checking the battery voltage while it's working, it's 8.55, and we want to bias our transistor in the middle of that. So that's going to be 4.27.5. I put the gain control on this thing here because we want to use that, but this trim pot we're not going to use, we're only going to use it to bias it. We're looking for 4.27 volts. I did not give myself the luxury of adding the extra resistor to make the biasing easier, so it's very sensitive. That's close enough for me. Let's see what it sounds like. Okay, so I'm not directly monitoring my guitar. So you now hear it through my speakers, which is not ideal. But this already sounds quite loud. So now we can turn up the gain and see if that works. I got my gain control in reverse. The next thing I was wondering is if we can use this old capacitor. It's about 40% of the capacitance of the last one. Holds up. I actually hoped this would cut off more high-end frequency, because I wanted to show something cool that you can do with the input capacitor. So let me grab an even smaller capacitor. This capacitor is absolutely tiny. Yeah, that's too tiny. Let's try this 0.5 nanofarad capacitor. So I got my tiny capacitor in there, and you get a very twangy sound because it cuts a lot of that low end. Mangle a second capacitor in there, and then move our input pin. Add a little trim pot. With this trim pot we can hopefully switch between the tiny capacitor and the big one. And this can be our low/high button. So the reason I made it a trim pot is because it takes up less space, and I will decide later if I want to make it a knob like this in the final design. I think this one might be a bit too big. So here we are back in the editor. In a bit you'll see me assemble this circuit. We have our preamplifier here, we have our high pass filter here. I set up a thingy that allows you to play a chord or a single note with this switch. This is a power chord. Here we have a second amplification stage, and here I'm not using the capacitor trick because I want to have my gain be able to go up to the point where it completely goes over the voltage limit, so you can get that really gnarly zappy sound. That's the best I can emulate it. Eating some popcorn. So let me first talk quickly about this high pass filter, because I really don't like it. The idea, I thought of this filter myself, and then I realized it's also on Josh's channel, or GHS pedals that I mentioned before. But I did think of it before I saw it there. But it sucks. I've never told you what a spectrograph is. Let me do that first. It basically shows you what frequencies are present in our signal. So I'm playing only two frequencies, this one and this one, but the distortion causes these other frequencies to be here. If we listen to the sound now, you hear that's more than two frequencies. I can also click show voltage and then it goes back to this, but I like seeing the spectrograph here. I can add a frequency. This third is a bit too much to handle for it. So let me first explain the idea of this. The idea is that you can smoothly transition between the big capacitor and the small capacitor, but in practice, either you make the resistor too low and then you just send the signal through both capacitors anyway, or you make the resistor too high and then you mute the sound way too much if you put it halfway, so you cannot blend smoothly in between them. So I really don't like this high pass filter here. So I also had the idea of putting the diodes on a variable resistor, so you can kind of choose how much you want the diodes to be able to steal. But I also don't like this because the same reason as this one, these variable effects just are difficult to make work correctly. In the end, I also added in this low pass filter. So a little bit about filters. Filters you can put anywhere. You can put them in between any. I could have put this filter at this capacitor, for instance, or at this one. And it changes the sound where you put it, of course, because as you can see in the spectrogram, the distortion adds frequencies, and filters change the height of frequencies based on how large they are. I might do a video on the mathematics of capacitors, and then I can also talk a bit about filters. So this little application here also has some cool built-in effects. One of the preset circuits in this app that I thought was really cool was this, what do they call it? So what this filter does is it splits your signal into three based on the frequency. It uses inductors, which I have, of these values approximately, but I haven't talked about inductors yet. I might do that on the same video that I talk about the mathematics of capacitors. That seems like a good time to talk about it. So the nice thing about this second amplification stage is this first one has nothing to do with it, but we can still let the preamp determine the distortion. So let's check out some diode distortion. We're doing it live. Actually, I'm editing this. Not very convincing. Let me zoom in on this bad boy again. Whoop. So unfortunately the diodes are a bit underwhelming. I'm going to check out these silicon diodes instead of the Zener ones, see if that makes a difference. Seems to be just a transistor still. What I think is happening is that we are going over this transistor's limits somehow, causing it to clip way before it reaches a 4-volt peak ever. Luckily I have an ace up my sleeve. The internet is always raving about these germanium diodes. They should have a very low voltage threshold. Let's see if they do the job. They definitely do something. Still a bit concerned that we have to blow the gain all the way open to get that. Let's try pushing our second amplifier a bit more. So that's always fun to unbias this one. Let's try some other diodes now that I cranked up the second amplifier. So I do get why people like the germanium ones, although I do think it's a skill issue. You can get a very similar effect from these cheaper Zener diodes. You just have to make sure that you can pump a lot of juice into the circuit. So I think I know what I want for my final design, and I got there by just fucking around with it a lot. I'm still toiling over whether I want a tone control, like a low and a high end thingy. Okay, so this is where I'm at. I made the preamplifier, I made the second amplifier. I tried out some different diodes. But honestly, I just kind of winged the second amplifier and it doesn't work well enough for this terrible guitar here. So I'm kind of at a crossroads. Am I gonna improve my old guitar or am I going to change up the design? I'll show you what it sounds like with the good guitar though. That's horribly biased. Now it just sounds like a building falling down. But you cannot get that sound with the other guitar. So on this guitar, which I prefer playing, which I'm not complaining about, but I wanted to be able to go crazier. Oh, it can go crazier. Haha. think it's to the drawing board, see what I actually made, do the editing that you've probably already seen, and so the biggest problem I have now is I can make it sound classy and like a building falling down, but I have to tune multiple knobs and I want it to be one single thing that I can turn. So we're going to think about how to do that. Before I go to bed, I've added one last feature. This is what I had, but I added this low pass filter, which can give you this more smooth quality. So you can compare it maybe to the tone knob, to the tone button on the guitar. This is the tone button. I am debating whether I should add it as a feature or not. With this huge amplification, I was wondering if this tiny piezoelectric element could also be properly distorted. Unfortunately, got rid of my peak detector, so I can't measure the voltage, but I know it's not so big. Now I can record some sick riffs on this classical guitar. Or I can play some very interesting Villa-Lobos. Which honestly sounds like shit. But maybe Targa works better. This is the point where I have to complain about something. I absolutely hate distortion. I think it's a terrible effect. I think it only works good if you use simple intervals like fifths and fourths. And most nice music uses the more fun intervals like thirds and like sixes. And distortion just makes those sound like trash, so it's a shit effect. I'm sure there's some uses for it. Jimi Hendrix is pretty cool. He can use it quite well, I think. Overall, not my favorite, but I do like the technology, so that's why I still enjoy making distortion effects. Also, this piezo effect works like a mic. So this is where I'm at the moment. My effect currently has 7 tunable resistors. There's the 6 trim pots, and then there is the gain control. 2 of these are of course bias controls, this one and this one. I'm just going to set them on the correct number when I make the final design. This is the input high. This is the gain control on this transistor. This is the resistor that determines how much the diodes are allowed to steal. This is the low pass filter with this capacitor here. I think I'll end this video here and I'll maybe update you on the progress of this design in a later video. And I can do a tutorial how to do a strip board, for instance. Sorry for the truck in the street. See you in the next one.